Okay, I'm not here for that. So what I'll do is I'll go through the solution to the last thing we did, and then we'll carry on with the rest of the material. And I'm sure we'll pick up some more comments and things as we go on. So I'll just start with that and see where we go to. So where were we? So there's a problem with Emacs. Just leave those behind. Okay. So we'd run quite a simple. We'd submitted quite a simple job, just around this XT high executable that was supposed to fault binding. Okay. And looking in the output from this, so output from the job, you can see what it does is it gives you a summary of which nodes are in use, which nodes you've got access to, and I got these two nodes, how many MPI processes and how many OpenMP threads and what the name of the executable was on the two nodes, which is the same in this case, and then tells you that it gives you some sort of summary around how the processes and threads, but we don't have any threads in this simple example, are bound to cores. So it says on node 0, rank 0, which is process 0 from MPI, and thread 0, because there's only one thread per process here, are bound to core 0, and so on. They're bound sequentially through all the cores up to core 127, and then you move on to the next node, and you'll see that the next rank in the next process is bound to core 0 of the second node, and so on. So this is what we'd expect, given the options we'd supplied and how I described it worked. Described it worked earlier. Okay, so that looks fine. Okay, but we've spoken a bit about before lunch. We spoke a bit about some questions around memory usage and making more memory available and things like that. And obviously there are the high memory nodes where we can do that. In fact, let me just do that. Okay, what we'll do is we'll try submitting this job to the high memory nodes and see if we can get it to run. Now, the high memory nodes aren't available in the short QoS, so it may be that I just end up queuing for a long time waiting for an available high memory node, but you never know. You can sometimes sneak a job in if it's a small one. So I'm going to copy test job to Slurm to high mem job Slurm. I'm going to edit that file, and what I'm going to do this time is I'm going to reduce it down to one node, which gives me the highest chance of running. Change it into high mem job. We've got 120 plus nodes, that's fine. CPU tasks, okay, accounts, all that's fine. Things we need to change are the partition and the QoS, so we're going to change that to high mem, and the same for short. We change that to high mem as well. It's going to do exactly the same thing. The only other thing I'm going to do is I'm going to do I think there's a command. Oops. Yeah, so we'll run this command just to show how much memory is available on the node as well in the job, just to check it's a high memory node. Okay, so that'll print out how much memory is available on the node as well. Okay, so I'm going to sbatch. Okay, so you can see it's queued. It needs one node, but jobs. There's some jobs already running, so I'm not getting access to it straight away. Oh, there we go. It started now then. So it has actually just run. And now it's in CG state, so it's exiting. So we hopefully should have the Slurm output. And 837 was the job ID for that one. So you can see at the top here, this is the output of the free command. You can see the memory is 512. Right, this is the output in memory, but you can see not all of that's available, obviously, because some of it's being used already for OS processes, and the binding looks exactly the same as the other one. It's just it'll go up to one node. Okay, so the high mem, you just change the partition and the QoS to high mem, and you can access those nodes directly. But the other way to get access to more memory, which may be one problem with the high mem nodes is if your job's very large, there's only 500, just almost 600 of them available. So if you've got a job larger than that number, you're not going to be able to run it on the high mem nodes because there aren't enough of them available. But also, if you want a large a reasonably large fraction, or you're running a lot of jobs, then it can be quite problematic queuing for the high memory nodes, in terms of demand for that sort of resource, because it's a restricted resource on the system. And it may be actually that you don't scale to that many cores anyway. So waiting might not be the way to go. But what you can also do is underpopulate a node. And by underpopulation, I mean generally not using all the available cores on the node. And this means that you increase the amount of resource available to the cores that you do use. So that resource can be memory capacity. So you get more memory capacity per core, or it could be memory bandwidth would be another one. You get potentially more memory bandwidth per core as well. Though how you take advantage of that depends a bit on the pattern of mapping cores, processes to cores, and numer regions and things like that on the node. But you could do this by altering. If you remember in our job here, so I'm going to make a copy of our test job to underpop job.slurm. So this is our job we started out with before. So we've got two nodes here. So you remember we specified how many tasks or how many processes we wanted to launch per node. And if we launch 128 processes, irrespective, without not worrying about threading and things like that at the moment, then we're using all 128 cores per node. So what we actually do to underpopulate is we change this. So we only say we wanted to half populate, double the amount of memory available per process. We'd only use 64 per node. The other thing we want to do is set the CPUs per task option, and to make sure that we set the stride so that the processes are evenly distributed across it. Now, this isn't always necessary, but particularly if you're wanting additional memory bandwidth or memory capacity, it makes sense to distribute the processes as symmetrically as possible across the node, so they have access to the memory in a symmetrical way without having to go via other pathways. So let me try and get a better idea of what I mean here. So I'm going to go to the user documentation here. I'm going to go back and I'm going to go to the hardware section, which has this picture as well, but it also has a picture of a compute node. Okay, and this is a bit complicated, but in each compute node, there's the two sockets with the two 64-core processors. Okay, and if we look at a particular 64-core processor, so in each of that, it's divided into these numer regions, which have direct access to particular amounts of memory, the DDR, which is the normal RAM. Don't worry about the other pictures at the moment. So each block so there are 8 blocks on a node, 4 per core, 4 per processor, that have direct access to memory. What that means is that if you say you underpopulated a node by half and you put them all sequentially across the first 64 core, the first 32 cores on a processor for the first half, or the first 64 cores, then you just fill up one processor, and each of those processes would have access to the same amount of memory in its own numer region, its own memory region, as it had before. If it wanted more memory, it has to go out into this I/O die, then off the I/O die to the other socket and out to the memory on this socket, which is a longer pathway, so the performance is going to be much worse. Okay, so if we could distribute them still evenly, even though we've half populated, we want to half populate each of these numer regions, of which there are 8 in a node. That still gives us symmetrical access to the memory capacity and the memory performance. Okay, and the way you do that is using the CPUs per task, which, if you remember, I mentioned briefly, sets a stride between process placements. So when that's 1, you place them sequentially on cores 0, 1, 2. If you set that to 2, you place them on cores 0, 2, 4, 6, 8, so on and so forth. And what that stride does, it means you actually fill up all of the numer regions, but half populate each of them with processes, so you keep the memory access symmetric. The easiest way to remember this about keeping things symmetric is that when you multiply these two numbers together, you should get the total physical cores on a node. So 64 times 2 is 128. Okay, and you could use other combinations as well. So let's change that in our job script here. So we've got 64, we've got 2, we're still only using one thread, so this is just using half the number of processes each node. So what this means is instead of 256 processes, we should get 128 in total. So let's submit that and see what the output shows us. So it's still pending, running on 2 nodes, still running on 2 nodes, still running. It's taking quite a long time, this one, for 30 seconds. There you go, that's it exiting now in CG state. Okay, so let's now have a look at the SLAM 855, and it was 862, this one, and see what it says. So the node summary is pretty much is quite similar. The only difference is is that we're running only 64 processes per node. Okay, the number of threads is still the same, and you can see now that the thread affinity actually, rather than just being pinned directly to core 0, it actually says it can use core 0 and core 1, and then the next one could use core 2 and core 3. So each of the processes has access to 2 cores in the NUMA region. Okay, and it can potentially migrate between those cores and depending what's efficient. And generally they won't during the program, but it uses during the program execution. But it makes sure that each of the processes span all of the NUMA regions. You know, each NUMA region has an 8 for the processes, so 8 processes per NUMA region. Okay, which means that you get equitable memory bandwidth and equitable memory capacity across the processes, across the 2 nodes. And you'll see in total there's 127 ranks. So what you've done is you've halved your number of processes, so halved your parallelism, but you've doubled the amount of memory resource available per process. Okay, and so as I said there, so I'm not going to labour this point very much, but you know, you should be able to think quite quickly. I mean, you can try running this if you want. You can have a go at it, or you can just type the answer in the chat if you want. What would you do to run on 4 nodes with 32 processes per node? Anybody willing to have a stab at that one? What the options would be for your job script? No. Okay, well, what we do for that one, I'm just going to actually edit my job script and do it. So under pop job, so we want 4 nodes, 32 processes per node. So that bit's pretty straightforward. 4 nodes, 32 processes per node. And the only other thing we do is we modify CPUs to task to distribute them evenly. To get to 1 to 8, it's 32 times 4. So that goes up to 4, like that. Let's try that again. Okay, so it's just waiting to start, and there's always a bit of a delay with things starting as the scheduler catches them. So this time it's 882. Okay, so now we've got 4 nodes, 32 on each node, and you can see the affinity now is from cores. It is across 4 cores. So each NUMA region has 4 processes in it. Okay. And that's what the solution says. Okay. I'm going to get rid of it because it's quite long. Okay. The other use you'll find for this sort of what looks like underpopulation but isn't. The other use where you'll see this reducing the number of processes per node and increasing the stride, CPUs per task, is when you have hybrid MPI and OpenMP jobs, when you're using both threading, OpenMP threading, and MPI parallelization. So you have both processes and threads at the same time. In that case, what you're not doing is binding a particular process to a set of cores. You're going to use these core, and potentially 3 of the cores will be idle at any one time. It could be any of them. Instead, those cores are going to be used for the threads that run per process. So the way this hybrid works is every process has a number of threads associated with it. And the main difference between the underpop, so let me copy that one across. So I'm going to copy my underpop jobs.slam to hybrid. Okay, so the difference this time, this is a pretty common, this is actually a good place to start. Right, we want 4 nodes. We might want 32 processes per node. And then we want 4 OpenMP threads per process. So the difference from the underpopulation one is these options all stay the same. We're going to change the number of OpenMP threads to 4. So that sets the number of threads that get launched for each process. And we need one other OpenMP variable, which is this OMP places cores. What that says is that I want to place each thread on its own physical core, okay, to make sure they're pinned properly. So if I run this one, you should see that the output is slightly different from the pure process one, where you're really just underpopulating. In this case, we're using all the cores on the node, but it's just some of them are for threads, and they're for threads rather than just leaving some quiet. So let me submit that one. So that's 889. Oops. Oh, it hasn't run yet. It might take a bit longer to launch because it's got threading in it. Oh, here we go. So this time, before, if you remember, it was MPI 32 OMP equals 1. This time I've got MPI 32 equals 4 on each of the nodes. And then now the affinity looks slightly different. Okay, so on node 0, there's each rank 0 has 4 threads associated with it. 0, 1, 2, and 3. They're pinned to the first 3 cores. Process 0, that is, rank process 1 has 4 threads associated with it, again 0, 1, 2, and 3, and they're pinned to the next 4 cores. So in this case, the CPU's per task, the stride, isn't just distributing them evenly across the new regions, though it's still doing that. It's making the gap for the threads to slot into when you run in this hybrid manner. Okay, and there's some description of there. This is a slightly different example with MPI 8 to OMP 16, but you can see the output looks pretty similar to what I was showing there. It's just that there's slightly different numbers. Now, as I've just shown you, each ARCHER2 compute node's got 8 of these NUMA regions, 4 per socket or 4 per processor, and with 16 cores in each of these regions. And programs where the threads of process span multiple NUMA regions, the same as underpopulation, because of memory access, the same way as we do when we underpopulate, are going to be much less efficient. So yeah, the general idea is you use thread counts that fit well in the ARCHER2 compute node layout, and that effectively means it's one of the following options for hybrid jobs on nodes when you use all cores. So you could have 64 MPI processes and 2 OMP threads per process, 32 and 4, which is the example we had here, 16 and 8, or 8 and 16. If you're outside those options, in terms of using all the cores on a node anyway, obviously there's ones where you don't use all the cores on the node, which can work too. Then they're really your only 4 decomposition options between threads and MPI, including threads and MPI processes as well. Okay, so it does get, once you're underpopulating or using hybrid, you do need to start to think about what the architecture of the node looks like and what that might mean for performance. And you have to be a bit careful about how you lay out the processes on the compute nodes themselves. Okay. So I hope it makes some sort of sense. I know it's a little bit fiddly, and particularly around how a node's made up. But I hope it gives you a flavour of what's going on there in terms of how the node architecture and the memory layout on the node actually relates down to what you see when you actually try to run programs that don't use which don't use just essentially 128 processes per node, which is probably the most common way of using things. So we're getting towards the end of the scheduling section. Now, there's a couple of extra topics that I want to talk about. One is these interactive jobs and using srun directly. And the other one, which isn't in the documentation, which isn't in the course materials, but I want to cover as well, is using the serial nodes, the data analysis nodes, and because they're slightly different and are a feature on ARCHER2 that wasn't there on the sort of 4-cabinet system, which people have been using for a long time now. So we'll do the interactive jobs first, and then I'll talk about using the data analysis nodes. So sometimes you want a direct login on the compute node to be able to test things out interactively. You might want to run some commands, see what they give. You might want to launch some parallel programs and get the output straight away to help you either debug a program, or to actually just get a feel for what's going on and what different things might work and see the output in real time. It can sometimes be useful. And the way you can do that is, instead of writing a job submission script and using sbatch to submit it and then looking for the output, is you can use the srun command directly from the login node. And that allows you to run either jobs directly, or you can also get a prompt on the compute node where you can type your commands in. So we're going to show the first one. In the first case, I'm going to show you just launching the parallel program directly from the command line itself. So here we have we're going to do the same sort of thing as we've done before. We're going to run the test with 2 nodes and 128 processes per node. So this is pure MPI, no OpenMP threading, no underpopulation, nothing like that. Now, of course, because you don't have the job script to set all the variables and things like that, you need to set these things on the command line before you launch. So we need to do that sort of thing. So we need to export OMP num threads equals 1. Oops, I can't spell that. Or have at least put a lowercase character in there to make sure we don't get any OpenMP threading in our program. And then we need to make the XT-high program available with the module load. Okay, so that's its own environment. These are the sort of thing, this is what you normally do in your job script. And then you can just use srun. And you can give it the same options that you had to sbatch, but you just need to get them on the command line. So, we're going to use partition standard, QoS short, 2 nodes, 128 tasks per node or processes per node, and one CPU task. We'll go to 10 minutes again. So I've got all those options, and then I'm going to say the account's different from the example there, TA045. Oops, can't type that either. And finally, the executable you want on XT-high. Okay, so there's no difference there apart from it's a long command line. They're the same options we've been using for the other ones, so let me do that. So it tells you your job queues and weighted resources. This time it doesn't give you the prompt back because it's an interactive job. So now it's been allocated, and so it's starting to run. And if we just wait and keep running, keep waiting, and hopefully it'll run and we get the output straight to our terminal because that's where standard out is. Okay. Now, you may notice that something's slightly different from when we ran it non-interactively, because if I scroll all the way back up here to where we first had the output from our first job. So there's our first job there. I'm checking the progress, standout, standard error. Let's see what it looks like. Okay, so this is what it looked like when we ran what we think is exactly the same, 128 processes per node across 2 nodes in a batch job. You can see that the affinity is slightly different here. Okay, so there's only one number here, and each of these is bound to 2. And you can see that they're bound to 2 separated by a number 1 to 8. What you're seeing here is the hardware threads. You know, I said there were two, where we talked about there were 200, looked like there were 256 cores per node, and that was logical cores, not physical cores. So here you're seeing the logical cores as well as the physical ones, okay? And you're seeing that the ordering is slightly different as well. Okay, so core 0 and core 1 to 8 are both on with the same physical core. So it's physical core 0, essentially logical core 128. Right, they're the two hardware threads on the same core. So actually, the fact that it's bound doesn't really matter and shouldn't make much difference. But the reason that's different is because we didn't provide the hint equals no multi-thread to the S1 command here. You know, that was missing. That was in our batch script on the S1 command. So if I rerun this now with a hint with no multi-thread, hopefully we'll be getting closer to what we had before. It takes its time to run. Okay, so here we go. I've scrolled too far. So this time they are only bound to the physical cores. So we've got rid of that logical core bit, but you can see they're in a different order. And if you remember, I said that was what the distribution block thing was doing, was making sure we were in sequential order of binding processes to cores, which is not what Slurm does by default. Slurm does this sort of strange round robin. Now we talked about NUMA regions, you'll see that it's actually round robining on the NUMA regions. On half, yeah, on NUMA regions every 8 cores. Okay. Sorry, on half NUMA regions every 8 cores. 0, 1, 2, and so on and so forth. So we can get rid of that by adding back in the distribution block again, and we can try running that again, and hopefully we'll end up back at where we started from when we ran in the batch script. So yeah, and your command line was very, very long and a bit annoying to type out each time. Okay, so now we're back to this sequential assignment of processes to physical cores. Okay. So the other way you can use the interactive nodes. So if I get rid of all the distribution block, intelligence thread, and application stuff, I just need to remember the syntax for this exactly by looking in the documentation. The other way you can do use these is to actually get a prompt on the compute node, so you can launch things directly, and you can really test out what your job submission script might be doing interactively before you actually submit it. So I'm going to go down here. Somewhere down here, there's a bit about using S1 directly for an interactive job. Okay, so the option you need to add this time is this pty and the bash command. Excuse me. So what this is saying is give me one, so that's giving me 2 nodes. Okay, that's fine. Give me 2 nodes, n test per node 128, so 128 processes per node on this account. Give me a terminal, and the application I want you to run is bin bash. Okay. So hopefully if I run that one. Okay, you can see my prompts change now. So I'm still the same user, but now I'm on a compute node. Okay. And I can tell it's a compute node because one of the reasons is there'll be no home with file system mounted if I do df. I'll show you that you can't quite see it, but there's no home file system there. There's only the Lustre file systems, which are the work file systems here. But now once I'm on this compute node, I could type my commands. I could module load xt high export omp num threads equals 1. I could do all the things I'd normally do in a bash submission script. I could use the free -m command, show me that there's 256 gigabytes, not all of which is available. And I can now actually run xt high in parallel as well. So srun xt high. So I haven't given srun any options this time. So let's see what it gives back. So you notice this time when I was using srun, it's like I'm using it's the same way I'd use srun in a batch script. It doesn't seem to be working. I've done something wrong, Kevin, haven't I? Give me a second. Check I'm doing something stupid.
I didn't notice anything wrong. I didn't.
Okay. So that worked. Maybe I was just being too hasty. Let me try it without the oversubscribe this time and see if I was just not waiting long enough. I was just being too impatient. I'll give it a moment to run. So the idea is that once you're got a prompt on the compute node, you can actually just issue the commands you would have issued inside the job submission script to test things interactively. And in fact, actually, it tells me here. Sorry, it was the oversubscribed. I should read a note in the documentation. So you do need the oversubscribed flag. Is the only slight wrinkle. And then I want to the usual hint equals no multi-thread distribution equals block. Okay, so you do need to add this extra option, which is oversubscribed. That's because otherwise Slurm thinks things are already in use. Oh, I don't know. Did I mistype? No multi-thread distribution. Okay, that is weird. So I don't know why the hint no multi-thread's not working there. Or the distribution block isn't working either. That's interesting. I hadn't noticed that problem before, but I think I know how to solve it. So what that tells me is I need to add those options here. I think, but it could be also that oversubscribe blows them away. Let's try that and see what happens. This is what happens when you go off piste a bit. And so I'm going to do srun. Oh. I'm going to do export omp threads equals 1 module load xt high and then srun. Let's try that, see what that gives. Okay, that's better. Okay, so the options to srun in terms of placement and those sort of things need to go on the original srun, which gives you the prompt rather than the srun inside actually. So that's a mistake in this documentation that needs correct. I'll take a note of that and get that fixed in there. But what this does is you could get time on a node for as long as you want. I've only got 10 minutes here, so at the end of 10 minutes, I'd get kicked off that node. In the short QoS, you could only go up to 20 minutes. But if you got access to a node in the main pool, you could have access for hours, right, and do debugging, issue S runs, interactively check things are working, change something in your code or change something in your setup in your input files, issue the S run again, check the output, and things like that. So you can work in a bit more of an efficient way rather than having to submit jobs all the time to the queue. It can be more useful for when you're doing that sort of more interactive style work to do these sort of get this sort of access to a node. Okay, get rid of that. I'm going to go to the bottom. So we talked about interactive jobs via the direct S run, which was running STI directly. I've also shown you how to get access to a prompt on a compute node. The final thing I wanted to show you in this section before we move on was around using the data analysis nodes. So the data analysis nodes are slightly different. The reason they're different is because there's two of the nodes. They're designed for people who want to use small numbers of processes rather than 128 processes, which is a whole compute node. You might just want one because you've got just running a serial data analysis task or something like that. But you might need more memory than that. So what the data analysis nodes allow you to do differently is you can you request less than a node's worth of resources. Okay, so I'm going to make a separate directory for this one, just because. And I'm going to copy my test job slam to serial. Oops, I can't spell serial. Because I want to create a serial job here. You don't always have to be serial jobs from the data analysis nodes, but that's what I'm going to show you because it's the most common use case. Okay. So what do we need to change in here? So the name doesn't seem very appropriate. So I'm going to change that to analysis. It's going to ask for one node. And this time, I'm going to ask for one task per node. CPU's task one's fine. Time's fine. Account's fine. Partitions. Serial. Oops, I can't spell that word for some reason. Serial. Or I can't type it anyway. Serial. Okay. I don't want to use XT high this time, really. So I'm going to get rid of that. OpenMP threads isn't interesting to me. Because I'm running a serial job, I don't actually have to use srun at all because it's serial. So what I might do is just put a host name. But I could do you know, if we're doing data analysis or something, we might want to use Python. So let's try and get the version of Python. Maybe that'll work. Okay, so I'm just asking for one core this time. So let's try submitting that and see what happens. Should still be running. It's F16 now. So the SLAM output's in the same sort of way. Okay, so our host name was DVN01. For historical reasons, these are called data visualization nodes. That's how they're set up by HPE. That's what DVN stands for. And then the Python version I'm getting is 3.8.5. Okay, the only other slightly more complicated thing with the serial nodes is with this setup here, I get allocated a certain fraction of the memory of the node per core I ask for by default. So if I ask for a single process, a single core, then I get, I'm going to have to look it up so I don't make sure, I don't get the so I don't get the number wrong. It's in the data analysis section. Okay. Yeah, okay. So you get 1984 megabytes of memory per core, a little less than 2 gigabytes when specifying cores only. Okay. But I can ask for more memory than that. Say I had a serial process that wanted to use more than just under 2 gig, which I have that, which I get by default. I can say so this might work, it might not work. So I think I can ask up to 128 gig. Oh, there we go. 125 gig is the maximum I can ask for. So let me ask for 64. And that's a nice round number. For some reason, I have an aversion to asking for numbers that are powers of 2. Okay, so this should still work, but it would give me access to 64 gigabytes of memory rather than just the standard just under 2 gigabytes of memory. And that would have. And we won't be able to see that in the output, of course, but it should still run, I'm hopeful. Okay, so we get the same output, but we ask for more memory, so you could potentially access more memory when you're using the process on the serial node. So the serial nodes, you can use them in much the same way as the compute nodes. The difference is you can ask for multiple cores up to, I think, 32 cores is the maximum you could ask for in one single job. And you can ask for up to 125 gigabytes of memory for your on the serial process. You get a sensible default amount of memory. If you ask for a number of cores, you get just under 2 gigabytes per core. If you just asked for memory and not cores, you would get that memory and a single core. Okay. And as for the compute nodes, as we've just seen with doing interactive jobs and things like that, you can do the same things on the serial nodes. You can use so where is it down here? Yeah, you can use the same sort of srun command that we saw before with bash, bin bash, to get access to a prompt directly on the serial node. And also, you can actually send it this -x11 option as well, which will export graphics from the serial node or the data analysis node back to your desktop if you've logged into Archer with the -y function or -x, -y or -x option. And you want to display graphics, to say you're using Matplotlib or something in Python, and you want to see or pandas or something like that, and you want to see the data straight back, you could do that. As we've seen earlier, sending displays back across the internet can be quite slow and tiresome. Often when I'm doing that sort of data analysis, I'll instead just output the plots directly to a image file, like a PNG file, and then just access them instead. Because it's a bit quicker. Okay, so I think I'm sort of the end of the scheduler section. We covered a lot of ground in that section. We looked at the different Slurm commands, what type of nodes are available, and what the different states mean, how you look at what's available in the queues, so what's available in terms of nodes. We've looked at how to submit batch jobs, how to run interactive jobs, how to underpopulate, how to do hybrid jobs, and at the end we had a brief look at using srun directly to access to run on nodes, and also using the data analysis nodes. Is there anything else in terms of scheduler in particular that people want to know things about that I haven't covered yet? I'm happy to talk about it now before we move on to different sections where we're not talking about the scheduler anymore. Andrew.
Yeah. I'm just thinking, because I often use resources on Jasmine, and certainly a couple of the executables I use, you have to specify the processor type that the executable can run on. I think the executables that I'm using at the moment only run on AMD processors. And Jasmine's got both AMD and Intel architectures.
Yep.
So are the same commands or similar commands on Archer for specifying the type of processor?
So in some sense, probably yes, they are in Slurm, but in another sense, they're not of any use because Archer2 is completely homogeneous.
Right.
Every node has exactly the same type, and even exactly the same model of processor. So they're all AMD, and they're all I can't remember off the top of my head. I think it's 7742. So LS CPU on a node always gives you the information on the on the node. Every node has these 2 times 77
Right.
EPYC 74742 64 cores. So actually, so the flags are probably still there somewhere, but there is no different architecture on Archer2. So
Right. Okay. Thanks.
no problem. Yeah, the only other thing I can talk about at some point at the end, if people are interested, because I think we'll probably have some time at the end. The rate we're going, if people are interested in the thing we've been looking at a bit recently, are the commands to look at priorities and see who's next in the queue and those sort of things. You can do those sort of things in Slam quite easily. So I can show you them at some point if you want, if people are interested when we get to the end. Anyway, I will carry on for now. We've got a few bits and pieces, a few other sessions that are sort of less technical information at the end here. What this one is labeled how to be a good Archer2 citizen, but actually it's a sort of tips for using HPC in particular, and from the service, I guess, from a service perspective, but also things that might help you out as a user. So rather than a good Archer has to be a good Archer2 citizen, which people generally are, it's more of a tips of what to do. The first one is around login nodes and what should I do, what shouldn't I do on login nodes. I think most people who've used HPC for a while have either experienced sluggish response from login nodes, which are often to do with what other people are doing on the system, or they've been inadvertently the cause of something and had maybe a message from the system administration team or the service team saying, sorry, we've had to kill some of your processes because they were causing this problem, XYZ, for the users. Because Archer2, when you get compute nodes in particular, that you're never sharing with another user the resources. The only resource you're sharing when you have access to a compute node, really, the only resource you're sharing are file system access. So if you put an excessive load on the file system, it can slow down processes potentially for other users as well. And interconnect access to the slingshot interconnect, where certain programs can cause certain communication patterns can potentially cause problems for the users. And in some sense, both of those, certainly the interconnect one is sort of not your problem, right? The interconnect should deal with it. It can be that a program can be pathologically bad, and then the CSE team will often work with users to solve things like that. For the file system, it's much easier to try and scale up and cause excessive load. But again, we can help people with those sort of things. But on the login nodes, generally, is the only place you're usually sharing with other users. Maybe the data analysis nodes are the other place. And what we try to do as a service is set them up in such a way to try and take the problem away from the users as much as possible, so they don't have to be as aware of what they're doing. So we use something called C groups, which tries to limit the amount of resource that any single user can have to dominate and cause problems for other users. So what this means is, you can expand into what resources are available on the login node, but when it gets to the level it's being a problem or other users are asking for resources, well, then it'll scale you back and try and limit the amount of usage you have of, say, memory and CPU and things like that. So it's quite powerful. It seems to work quite well, but it is not foolproof, and you can still potentially cause problems for the users if you run inappropriate things on the login nodes. So it says, here it says don't run jobs on the login node. On Archer2, that's actually helped a bit by the fact that if you try to run an MPI job on the login node, it just won't work because MPI doesn't work on the login nodes. It only works on compute nodes. So that helps us out on that situation. A lot of other types of HPC resource that aren't Cray systems, you can run MPI jobs on the login node, and that can cause that allows people to cause problems more easily for the users. But on Archer2, that's not possible. But generally, you're trying not to use huge amounts of resource on the login node and stop the resource. Nope, this thing's a bit broken here, but yeah, there's some example commands here about which would be okay to run a login node and which ones aren't. And things like something that's called physics sim. It doesn't sound like something that's really a login node thing. That sounds more like a compute node thing. Makes a perfectly normal thing to do to build programs. That's fine. Create directories.sh could be okay, but it might need tested. You know, if it tries to create like a million directories, it's going to cause a big problem. You know, so automated scripts that do things like make directories and things like that do have to be carefully tested before they're used in production, and maybe issued in a sort of dry run scenario where it tells you what commands it's going to run before you actually run them. Molecular dynamics doesn't sound like a compute node thing, and archiving, extracting an archive sounds perfectly reasonable. You know, that's something that could be done on a login node. Though you may find better performance on a data analysis node if you're doing something that's very big in terms of manipulating data, creating archives and extracting archives. Depends how big the data is. Because it's quite hard sometimes to keep a terminal session open for, say, 10 hours or something like that if your data extraction or data compression or archiving is going to take that long. You know, you could then now submit that to the data analysis nodes in a job script, the tar command, with a 12-hour runtime, and just leave it going. And then you don't actually need to keep your terminal open. So, you know, trying to avoid CPU intensive stuff, memory intensive stuff on the login nodes is good for you because it'll stop you getting frustrated when things don't work properly, and good for the users because it stops it affecting what other people are doing. You know, it's reasonably often now we get an email into the service desk with somebody saying, "Oh, the login node's a bit sluggish. I've had a look at top and user so and so. Look at them. They're using massive amounts of CPU, you know, they're causing problems for everybody on the node." Well, I mean, two things here. One is that the way the C groups is set up, you know, people can use large amounts of CPU, but it will be automatically scaled back if it's causing a problem for you or the users. You know, there's potentially you know, I mean, I say it's not foolproof, so okay, it's maybe not that big. You know, there is a chance that it could still cause a problem. But the other thing to remember is the login nodes have 128 cores, just like the compute nodes, right? So here, you know, we have percent CPU, and once you get down to about like 5, where somebody's using the largest fraction, that's 5 cores out of 128. So actually, it's not really a very high load average. Here you go. See the load average up here? That's in terms of CPU. So the load average is around 6 CPUs out of 128. Okay, so it's nowhere near overload this system, whereas we'll often get emails from people saying, "Oh, Johnny's using 100% CPU, they're causing things to be slow for me, please stop it." More often than not, if you see slowness on login node, it's caused by people. It's almost always when you're in the work file system, trying to access files in the work file system, and there'll be somebody doing something very IO intensive from a large compute job. That means that the response to the file system is a bit sluggish just at that moment because somebody else is doing something intensive, rather than anything CPU intensive or memory intensive that you can spot through top. So it's a bit misleading, top in that sense. Okay. So that just reiterates, I mean, the biggest bone of contention usually between users on ARCHER2, certainly on its predecessor Archer, is file system access. You know, and somebody doing something in a large compute job can affect the responsiveness of the parallel file systems, the Lustre work file systems, on the login nodes as well for everybody else. If you do see performance issues with a login node, please do report them. You know, I mean, we have quite a lot of monitoring on the system to try and spot issues as they occur and deal with them without having users noticing or having an intervention. But users are often on the system a lot more than us as service staff generally, other than our automated monitoring. So can sometimes be the first people who spot a problem arising. So if you do see something, please drop us a line because it is useful for us to get that feedback because, you know, we're not always logged on 24 hours a day typing ls commands to see what the responsiveness looks like. The only final thing is we don't generally allow outgoing SSH connections to other systems, using ARCHER2 as a hop host to access other systems. You can, of course, download data, SCP data from external systems and things like that, but interactive access to an external system with hopping via Archer 2 is generally considered a security risk for the service, and so if we spot if such connections happen and we spot them, and they're liable to be just being killed without warning. You know, if you're trying to achieve something and it seems like the only way to achieve it is to SSH out from Archer 2 itself to another system, then get in touch with us and we'll help you find a better solution, because that just generally won't work from the system. This is obvious, but an obvious tip, and you know, you say this to people in courses and out to people: don't share your login credentials with anybody. You know, it feels like such a mad thing to say. Well, why would anybody share their login credentials with anybody else? But the number of times we see people who've shared within a research group access credentials to Archer 2, so that they can log in and run jobs while they're on holiday, or check jobs while they're on holiday and things like that. You know, that is just not on from a security perspective. It's easy enough, you know, if you're in the same research group, getting an account on Archer 2 is not particularly heavy overhead. Once the project's set up, you know, you can log in to save. It's all self-service. If you need somebody else to run some jobs while you're on holiday, you can give them the job switch. You can use shared folders to share the data, you know, and things like that, and provide them instructions how to do it. They do not need your login credentials to do such a thing. Okay. The same as we do sometimes people see people doing loopback SSH connections, logging into another user account on Archer 2 from one user account on Archer 2. Often people sharing a terminal and saying, "Oh, I'll just show you how I did it. I'll do it that way." Please open a separate window and SSH in directly using that separate window, because these sorts of loopbacks, you know, all it takes is for that account that you're using to be compromised, or sudo. For that account you're using to be compromised and have some sort of keylogger or something like that, and people can get access to your credentials to log into the system. So, you know, that approach is to be avoided. Instead, just open a separate terminal window and SSH directly into the user account from there. If you're sitting down sharing a desk, maybe that's a little less likely nowadays with the COVID thing and that sort of access. Another useful tip to consider, or a useful thing to think about, is this test before scaling. So it says, remember your charge for usage on Archer 2. Of course, that's not true at the moment because we're in this free access period and with the system just opening up. But essentially, in general case, that will be true. You know, if you make a mistake in a job script, you know, it can actually end up costing you a large amount of resource, particularly as Archer 2 is such a large system. You know, so, you know, if you sit doing nothing for 24 hours on 1,000 cores, which is only 4 nodes on Archer 2, right? Because there's 128 cores per node. So it sounds like a large job, but in Archer 2 terms, with almost 6,000 nodes, you know, 4 nodes is not a very big job at all. But there's potential to waste a lot of resource, you know, just because of a typo in a job script, just lets it spin, you know, for a long time doing nothing. Or one where you mistyped the number of nodes you're requesting, but you know, there's either a 0 on the end by accident, or heaven forfend a couple of zeros, you know, there, and you're using a subset of them actually in the job. You know, the potential to waste resource is quite high on the system. And the problem where this really becomes a problem is you often see people write scripts that automate job submission. You know, you're doing a parameter sweep over lots of different values of parameters. You write a little bash script that just says, you know, change the parameter in the input file, submit the next job. Change the parameter in the input file, submit the next job. So, because I don't want to have to manually submit, you know, 250 jobs or something like that. And they're a typo in your job script, right? In the template of your job script that's getting submitted can lead to all sorts of problems, or a typo in the job, in this meta script that's submitting the jobs that submits 1,000 copies instead of 100, for example, ends up costing you a lot, and it's really annoying because you just have to do everything again often, or you've just lost the core hours, and it's frustrating for the users because all those jobs ran and blocked up those nodes that they could have been using, and they weren't doing any really useful work anyway. And my final this is the one that hurts me the most and drives me mad. He ends up with the swearing and the throwing things at the computer screen, sort of thing. Is the submitting a job, waiting days for it to run, and then it fails me in the first 10 seconds because I've done a typo in the job script. That is unbelievably frustrating. What I'd say is, try using the short QS. You've seen today, I've been using the short QS, and hopefully you've been using it a bit as well. Jobs run instantaneously there. You don't need to actually run any sort of real calculation. You just need to run the first, for most typos, running the first 5 minutes of a job is enough to pick up the fact that you've given the wrong executable name, or your input file's in the wrong location, or you've typed the wrong thing in your job script in terms of setup or something like that. Almost all of those are picked up in the first 5 minutes of running your job. So, especially if you're going to submit a large job or something that you think might take a long time to queue, it's worth just dropping one in the short QoS in the first instance to check that there's not just a stupid typo somewhere, and it's going to stop it running straight away as soon as it starts to run. And so I'm definitely an advocate for that one, because the number of times I get that wrong and just have a typo in my script and then it goes wrong is unbelievable. I mean, I've been doing this for years now. I still do it all the time. Okay, so this is the point here. You've actually seen it today, right? Use the short QoS, and you don't even need to change your job script. I mean, here it says change your job script, but as I pointed out earlier, if I have, so let me get my standard test job, that's just the original one we had. Okay, I'm going to change this to standard, which would put it into the standard QoS, which means it'd take longer to queue because I'm potentially run larger jobs, blah, 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 all that sorts of stuff. But if I now do that, the fact that I've written QoS short here overrides the QoS equals standard inside the job script. Okay. And hopefully it's still queuing a bit. It's just taking a bit of time to go through, and then it starts straight away. Right, it is in the standard partition because both short and standard are in the standard partition, but that's gone into the short QoS and hence has started straight away. So you don't even need to change your job submission script to test in the short QoS. You just need to add the command on the command line. You could even write a command that was something like dispatch test, right? That just had that QoS short built in or something like that you could then use to test quite easily. My next points are going to be about data. We're right back at the start. Sorry, maybe a question. Yes, allowing for timer as well, Kevin. You're right, of course. So Kevin's right. I would have also had to have, say I made my time longer. It's normally a 12-hour job. Okay, what I'll get now probably is it'll say, that's not allowed because you're running for too long. So I will also have to change the time here. Okay, and that'll let me submit. Okay, so Kevin's right. It's maybe a bit more complicated than I said there. So we talked about data right back at the start of this course, and I talked about data management plans and thinking about your data a bit. All these points are about data as well here. So we've got having a backup plan. The ARCHER2 home file systems are backed up. The work file systems are not. Even in the case of the home file system, it's worth remembering the primary responsibility for data on the system does not lie with the ARCHER2 service. If things fail, if backups fail, if all those sort of things fail, it's not ARCHER2's responsibility to protect your data. We always do our best, and we want to run a good service, but things happen sometimes, and your data is primarily your responsibility. If you have critical data, things that are, if you lost them, we all hear the stories about people who have their PhD thesis just stored on their laptop. They drop their laptop and it breaks, or they leave their laptop on a train or something like that, and something horrible happens like that. The same is true of data on the system. If you have critical data that would cost you months of effort, say, to regenerate, and is incredibly important to you, then don't just leave it on the HPC system. Keep copies of it elsewhere in secure locations. It depends on data. Of course, there are issues around data volumes sometimes, but if your data's not too large, you can copy it off. If it's really quite small, you can use version control systems such as Git and GitHub to export data quite easily and sync data backwards and forwards between different systems and between ARCHER2. You can check in things on your laptop and then just do git pull ARCHER2 and get the file data copied across, and you don't even need to worry about SCP commands and things like that. And it can be very useful for storing job scripts, analysis scripts, small input files, a record of the workflow that you did. For large amounts of data, you need to think a bit harder and have some sort of robust system in place for taking copies of the data off ARCHER2 to ideally backed up storage of some sort. Tools such as rsync can be really useful for this because you can use them to only copy across the data that's changed, and you don't need to do the analysis of which files have changed and things like that. rsync can do it for you and keep a copy in 2 locations. And finally, access to ARCHER2 is often time limited, generally time limited. In fact, most people, it's definitely time limited because the system will shut down at some point in the future. So it is really time limited for everybody. You need to have a plan to get your data off the system before your access finishes. The time transferred large amounts of data is generally large, not necessarily because the network performance is poor, but because there's a lot of fiddling about and babysitting and those sorts of things needed by the researcher and the user to make it work and to keep it transferring and to keep the throughput up and all those sorts of things. So make sure you've got a plan for this. The ideal way to do it generally is to ameliorate the transfer costs across the lifetime of the project. So have a plan where you're constantly transferring smaller amounts of data off rather than waiting at the end and trying to do everything in one big bang at the end. So it makes sense to think about this at the start of your ARCHER2 use and go from there. There's a link there that's not a link that needs fixed as well, but the actual link will work if you copy and paste it. There's some information in the using best practice guide on managing and transferring your data. But as I say, your data is primarily your responsibility. We do our best not to lose data, of course, but we don't guarantee that the data will always be accessible and be there. And my final point is a data one as well. It's about transferring data, and I've spoken, I think, a bit about the big overhead often is researcher time in transferring data, and that's certainly true. But there can be other bottlenecks as well in terms of technical bottlenecks, in terms of moving data, and actually. The bottlenecks are not always where you think. It's not always the network speed. As we saw earlier, I talked about encryption algorithms right back at the start, and we talked about compression when you're creating archives in particular, and when you're using rsync, for example, you can enable compression on the fly, so it tries to compress data before saying it to minimize the amount of data that's transferred, whereas that's not always a great idea. But the other bottlenecks you might see technically are the disk speed. So while on ARCHER2 often, particularly the work file systems, are highly parallel, very high performance, file systems can support very high performance if they use correctly high data bandwidths. Unless the system you're transferring it to at the other end has the same sort of performance, then you may find that the disk speed at the end you're transferring to is the limit in terms of performance. Metadata performance is linked to this fact that I said there was a static overhead for starting up something like SCP. That same can happen on a file system. You have lots and lots and lots and lots and lots and lots of small files. You have just lots and lots of files in particular. And then these metadata options in terms of opening or listing or manipulating files as part of transfer can bottleneck your performance quite significantly if you have huge amounts of files. That's why it's often better to do the archiving before you transfer, especially if you've got lots and lots of little files. And as I mentioned above, in terms of login nodes and shared access, these metadata operations performed by other users on ARCHER2 can also interact strongly with your work. So if somebody else is hammering the file system, particularly the metadata server, you know, opening and closing lots of files, creating lots of directories, deleting files, listing files, getting data on files, things like that. Then the more of those sorts of operations you're performing, the more likely you are to be impacted by people, other people doing things, and the more variable performance you're going to see. So, you know, combine lots of files into larger single files is the single best way to reduce your risk to being hit by these sorts of performance issues caused by other users. Network speed is obviously the one that most people go to. The network connection port ARCHER2 has really high performance network connections to Janet, the UK academic network at the moment, and supporting up to 100 gigabits per second from login nodes and from data analysis nodes. But the performance is actually limited by the slowest point along the whole line from where you're transferring to. So I've got my laptop here. I'm working from home, obviously, because we're in this COVID world, and so my laptop is sitting on Wi-Fi from my home. So the bottleneck in data transfer for me, most likely to transfer large amounts of data from ARCHER2 at the moment, will be the bandwidth of my Wi-Fi network in my house. Okay, so you know the transfer of ARCHER2 into Janet will be blazingly fast. You know, most ISPs, internet service providers, have good links into Janet now, so you get pretty fast there from onto Virgin, who I use for my ISP. So I'll get pretty fast data connections into Virgin. My Virgin rate to my house is pretty good, I think. So I'd probably get good, especially download rather than upload. I'd get good download speeds into the house, but then when it hits my Wi-Fi router and needs to go through the air to my laptop, then that'll be the limiting factor, because that's going to be the slowest one. Okay, so being aware of what the points in your network are. Often, you know, data transfer from data center to data center across academic institutions is going to give you the best performance without using things like workstations, laptops, individual personal computers in the way. And finally, firewall speed. This is a slightly odd one, but almost all modern networks have some sort of firewall that filters out malicious traffic. And that does have an overhead and can result in issues with data transfer performance. And most networks are not optimized for large data transfers. So if you go see data centers where there's large amounts of academic data moving around, so Jasmine down where the climate data is hosted, for example, will have you know, a special way it's set up in the data center so that it avoids the sort of general purpose firewall, and either has a demilitarized zone, which is outside the firewall, or it has a specialized firewall that's configured in a different way to allow large volumes of data transfer. ARCHER2 is exactly the same. You know, you have a special configuration and a special setup that's optimized for a different thing than usual networks are configured for. But that may not be the case if you're going, for example, you plug your laptop into the university LAN, then you know that LAN is probably sitting within the firewall within the university. So transferring from ARCHER2 to your laptop or workstation in a general university building will probably hit firewalls. It may not be the thing that's the rate limiting step, but depending on how their firewall is configured, it may limit the highest bandwidth. It may limit the bandwidth you can get to below what you'd expect based on network speeds alone. So the summary from all of that is, you know, plan ahead. You know, think about data transfer. If you've not got much data to transfer, that's great, right? I mean, you don't have to worry about it so much, and that's really good. Look at you. If you do have to worry about data transfer, think harder about it and what that means for you. Think about how you combine files into single larger files and single larger archives to reduce the overhead of things like SCP initialization and metadata operations. But plan ahead, right? I mean, all of this is really be prepared. You know, it's the Scout's motto. It's think about the data at the start of your project rather than right at the end when there's a panic to move it, and do some planning. So that was quite it's quite long. That session is in some sense a lot of me talking, but these are the sorts of this section was distilled from the issues that we often see people having on HPC systems, and in terms of sharing login nodes around data and around testing and wasting occasion, the frustration of seeing things fail very quickly once you've waited for a long time to respond. So we tried to distill that down into a summary of things that we thought useful for people to think about. So it's be careful how you use the login node. Data on the system is your responsibility. Again, don't do stuff on the login node, and don't be a bad person on stuff on the login node. So somebody who wrote this obviously was having a bad day with the login nodes when they wrote this section of the training. Where are we? Okay, so we've got time for a short break now. I think we've only got a couple of short sections when we come back, so we're almost finished now. Obviously, I think with the amount of stuff we have left, we'll have a little bit of time before we're due to finish at 4 for me to cover any topics that people want to know more about that we haven't covered in detail, or cover things that haven't been explained properly. So if you've got any of those, please have them prepared for the last session. But I think we'll go for probably have a 10-minute break, and then we'll come back and do the last couple of sessions, see if there's anything else that people want to cover, and then finish up and let people away.